Okay, YouTube, in my last video we introduced the concept of a rational function where we have some function of the form y equals some function of x over some function of x, okay? And they were typically of the form, a over x minus h and then some plus k off on the side, or, we could say, specifically speaking, we say like a over x. The idea here, though, is that this is a pretty simple rational function. And what we're going to start to look at here, at least in this video, is we're going to have a linear function or a first degree function divided by another linear function or a first degree function. So keep in mind, this is not overall, generally speaking, polynomial over polynomial, but a linear over a linear, but this will kind of broaden our horizons a little bit with respect to how we understand these. So the first thing I kind of want to mention is this. With these graphs here, y equals a over x, we said, well, it was just automatically understood that you have an asymptote on the x and y axes, that no matter how big of a number you divide by on x, how far to the right or left you go on this graph, it'll never reach a height of 0. We got something to look like this, if a is positive, something like that, if a is positive. And then we say that, the simple fact of the matter is that x could not equal 0. We can't have x equal to 0 because it would be undefined. So then we got this asymptote here at x equals 0. So that dictated the behavior of our asymptotes. When you have at least something linear over linear, what you have to understand is that it's not necessarily going to be x equals 0. Can x equal 0 down here? I don't know. Maybe it would cause the bottom to be equal to 0, but maybe not. So what we're going to say are a few things about this. When you have a linear over a linear, first things first, the vertical asymptote, we're going to abbreviate that VA, is located where the denominator, okay, let's put it this way, located at x values for which the denominator equals 0. The denom equals 0. Okay, so we're going to look for vertical asymptotes by basically setting the bottom equal to 0 and then solving for the x value that causes that to happen, okay? And then the other thing we want to say about this is that the horizontal asymptote, let's make a little note here. We say the horizontal asymptote is located at y equals, and I'm going to say a over c to go with this note sheet right here, but what I want to point out a and c are, they're the leading coefficients of the top and the bottom. So we could say the leading coefficient of the numerator divided by the leading coefficient of the denominator. This is going to be where our horizontal asymptote is going to be located. So let's take a look at a function here. We say graph the function y equals x plus 1 over 2x minus 4, then state the domain of range, okay? First things first, before we go and kind of inspect this graph a little bit here, I want to point some things out. This is actually a function that is a linear over linear. So this is perfectly what we're looking at in this case. And we say, okay, well, one comment I want to make here, I guess, is just in general, if you can factor the top and the bottom and maybe simplify, but if you can factor the top and the bottom, you probably ought to. So we get x plus 1 over 2 times x minus 2 if we factor out the greatest common factor. And I notice that there are no common factors between the numerator and denominator, so I'm not going to cancel anything out. Okay, so going with this here, I'm going to say a few things. We say, first of all, the leading coefficient of the top is 1 and the leading coefficient of the bottom is 2. So in terms of the horizontal asymptote here, we are going to have a horizontal asymptote that is the ratio of the top coefficient over the bottom coefficient, or y equals a half. So when we graph this here, we're actually going to have to put in a horizontal asymptote that is a half a unit off of the ground. And so we'd say that this is y equals a half here, and this is our horizontal asymptote. So now the next thing we want to accomplish, and actually we probably could have done this first, but found the vertical asymptotes. We say that, well, the vertical asymptotes occur at the zeros of the denominator. So what we're going to do is we're going to set the bottom equal to 0, 2x minus 2 equals 0. And we're going to say, well, divide everything by 2 here. And then we would say, well, this would imply that the 2's cancel. We get x minus 2 is equal to 0. So it follows that x equals 2. What this means is when x is equal to 2, and you can easily check this, plug this back into the original denominator, you get 2 times 2 minus 4, you get 0. So we could say, well, then we say vertical asymptote at x equals 2. So we're going to go over to 2 and we're going to draw in this vertical asymptote right here. So basically, what I'm going to tell you about graphing rational functions is this. The very first thing you always want to graph are all of its asymptotes, because after this, what do we know about their behaviors? Well, we know they have branches and they're often symmetrical. And so here's what we basically do after this. Once we've found the horizontal and vertical asymptotes, we're going to just make a table of values and we're going to plug them in and we're going to try to find how our graph behaves through this. So in terms of what values would I plug into this table? Well, one thing I want to tell you right now is this. I'm going to plug this in right now. We say 2, undefined. The fact is, maybe our graphs, when you look at these branches, they're not very interesting as they kind of go out to the right and to the left. Where are they interesting? Well, they're interesting around here, maybe a parent function at the origin, but mostly around the asymptotes. So if that's the case and I have an asymptote at x equals 2, then what I'm going to do is I'm going to plug in 3 and I'm going to plug in 4. And I'm going to plug in 1 and I'm going to plug in 0. Essentially, I'm going to plug in 2 values left, so 2 left, and 2 values right of every asymptote. That's right, you can have more than one vertical asymptote. So let's just open up the door for that right now, but say that we're going to go 2 left and 2 right. So when we plug in 0, what I mean is you're actually going to plug it into the top and the bottom of this expression. So the original expression here, you guys, is x plus 1, and then we have 2 times x minus 4. The idea is that we're going to get, a number over a number. I'm going to cheat a little bit here, but basically if we plug in 0, we get, okay, so 0 and 0. Let's think about this. I would get 1 over, 2 times 0 minus 4 is negative 4. So I would get 1 over negative 4. And don't freak out about this. We'll just go up here. We'll say it's negative a fourth. So we say negative a fourth, leave it. If you're a decimal person, we can go negative 0.25. If you plug in 1 now, so I get 1 and 1. So I would get 2 on top, and then 2 times 1 is 2 minus 4 is negative 2. So I get negative 1 here. So negative 1. If we plug in 3, okay, so we'll plug in 3. 3 plus 1 is 4. 2 times 3 is 6 minus 4 is 2. So 4 over 2. So 4 over 2. Or we could simplify this. We could say it's 2. And then the last one here, we say, okay, I'll plug in 4. I can write all over this one because I don't need to erase. We say this would get 5. And then 2 times 4, that would be, what, 8? 8 minus 4 is 4. So we get 1.25. 1.25. And I want to check on this here. We say 2, 3, 4. You got x plus 1. I suppose that makes reasonable sense. That makes reasonable sense. So let's go ahead and plug in all of these points. Well, we have all these points here, not plug anything in, but go graph them. So we say 0 comma negative a quarter. We're basically going to graph these straight up the way they look. So 0 comma negative a quarter. We're going to go 1 comma negative 1. So there's our left side. And we say 3. We're going to go over 3 up 2. And then over 4, and then up 1, and then just a little bit more. And we could totally label all these. What I'll tell you is we often don't need to label them, but if and only if you took the time to table it out. If you did not make a table of values, well, first of all, you wouldn't know these, so make a table of values. But as long as you have a table of values, you don't have to label them on your graph. We'd say, here's our graph right here. Okay, so this is our special linear divided by a linear ratio case. Practice your graphs. And then the last thing here I would just say is just be able to state domain or range, which this would be all real x values. And then we'll put a restriction on it. We say except for x cannot be equal to 2. We found that out by setting the denominator equal to 0. And then we say all real y values except for y cannot be equal to a half, a positive a half. Our graph is always going to approach positive a half, but never quite get there. Cheers.